Hello YouTube, this is my second in a series of videos that I'm making on counting, but in this video we're going to focus particularly on the concept of permutations, okay? And so let's go ahead and start with this. When we say permutation, the first thing we need to associate with this word is this, ordering. Okay, so orderings of something. Okay, so let's say we had a bunch of different objects, and in this case we'll just start with a simple example. We say the letters A, B, and C. A, B, and C. And maybe what we want to do is determine how many different orders are there or that exist for us to put these three letters in, okay? And would there be kind of a nifty way to figure this out? But the important thing here is this. When we talk about permutations, we say that order matters, okay? So in this case, let's talk about the orderings of letters A, B, and C. We say we could have A, B, C. We could have had A, C, B, where A comes first. How about B come first? We say B, A, C. B comes first again, B, C, A. And then let's go C goes first. We say C, A, B, cab, or C, B, A. But you'll notice here that we have six distinct what we would call permutations. We say six permutations, or of course this word that we're associating with permutation, which is ordering, okay? But six orderings of these three objects, okay? The question is, could we have found this out in an easier fashion? And actually, if we were to describe this in terms of like the fundamental counting principle, which basically says this: if you want to find the total number of possible outcomes for a series of events, you just have to know how many ways could the first, say, event have happened, or say letter have been chosen, how many ways could the second letter have been chosen, and how many ways could the third letter have been chosen. So in this instance, we said there were three events. There was the first letter, second letter, and third letter, but choosing these letters. And so as far as how many ways could the first letter have been chosen, well, we say it either could have been an A, a B, or a C. So there were three possible outcomes for the way this first letter could have been chosen. But as far as the second letter goes, since we've already chosen a letter for the first spot, then we'd only have two of the remaining letters left to choose from there, and then one left to choose from here. So according to the fundamental counting principle, it's just the number of possible outcomes for each event multiplied together. We had six outcomes, which is the six we've got over here. So what I want you to recognize is this. This was a situation in which once we chose a letter from these objects, okay, n objects, here we had n is 3 because there are 3 objects, then there was one less to choose from in the remaining spot, and also one less to choose from in that next remaining spot, until we got down to this very last one here. And this pattern of multiplying in this fashion actually is special, okay? We call this a very, very special pattern of math, but we refer to this as a factorial, okay, factorial. So factorial, basically, let's start with this. We write it as n with an exclamation point after it, where n represents the number of objects, say, that we are, ordering or permuting or shifting around. So in this case, we would have had like 3 factorial. But the definition of n factorial, and this is read, n factorial, this is how you read it, n factorial. So we would say that 3 with an exclamation point, we would read that as 3 factorial. But it's basically this. We say it is the number itself, n. So in this case, 3 factorial would say the number itself, n is 3, times 1 less than n. So now we had 2, which is 3 minus 1. So really, n we have n times 1 less than n times n minus 1 times, in this case, down to 1, but we say times 2 less than n. And this pattern would continue, okay, until we got down to like 3, 2, 1. But the definition of factorial is something that we want to be very, very familiar with. And so basically, it is the multiplication of these integers starting with n, and then just multiplying by the next lower number, next lower number, next lower number, next lower number, down until we get down to 1. Okay, so 3 factorial is equal to 6. I think it'd be worth our time to kind of play around with a few of these. 4 factorial would say this is 4 times 3 times 2 times 1, which is really this original 6 here times another 4 is 24. What if we did like 5 factorial? I just want to show you guys here. We get 5 times 4 times 3 times 2 times 1. We get this original 24 now times 5 is 120. So basically what I want you to see is factorial grows really, really quickly. 2 factorial, however, 2 times 1 is just 2. What if we did 1 factorial? 1 factorial would just be 1. And very, very important that everybody, let's change colors on this one. everybody remembers 0 factorial. By definition, we refer to 0 factorial as always being equal to 1. So this being said, we're going to go ahead and put this idea of factorial and permutation to work. So let's go ahead and start by taking a look at a couple of examples here. But let's start with this. We say, all right, 12 runners are competing in a race. Okay, so we have our 12 runners here. We say, first of all, how many ways can the runners finish the race? So, we could write this out. We could say, okay, well, like first place. First place, we've got 12 runners to choose from. Second place, we got 11 runners to choose from. Third place, we have 10 runners to choose from. Fourth place, we have 9 runners left to choose from. This is going to keep happening. Using our fundamental counting principle, we just multiply the number of ways. We could choose first place runner, second place runner, third place, all the way down. We know this pattern is going to continue. We get down to this 3 to 1 fashion. So if we want to find the number of distinct permutations for this, we could just say that it's 12 factorial. And most calculators actually have a factorial button on them. Now I don't. Yes, we have one right here. We say 12 factorial, enter. And so it's going to give us this really big number here. We say 479,001,600. So 479. I think we had 0016. So we say 001600. In terms of how many ways could these 12 runners finish this race, there are this many ways that these runners could possibly finish this race. Okay, so a ton of different ways to do this. Just goes to back up that factorial is very large when you get into larger integers. But we say, how about this next question? How many different ways from 12 runners could 3 of the runners finish, say, first, second, third? Now this is a little bit different when it comes to this question. We say, all right, when we consider this, we have to consider the fact that we're only discussing, say, gold, silver, and bronze. So we say gold, silver, bronze. We still have 12 runners, and that makes a difference here. But we say there were 12 ways, or 12 runners that could have finished in first place, but now only 11 that could have finished in second place, and then 10 that could have finished in third. So now we get 12 times 11 times 10, which is significantly less than last time. 12 times 11, 12 times, we'll go back here, 11 times 10, we get 1320. So there are 1,320 different ways that these runners, from 12 runners, you could finish first, second, and third. Okay, so where order matters here. This can actually be generalized, and so this is a little bit different than 12 factorial. It's a lot like 12 factorial, except for we cut 9 and everything after off from like the original factorial expression up here. So in order to generalize this, we say, there's a way we can do this. There's this formula right here. And so this is something, if you're learning this, you'd want to write it down, but it says the number of permutations or orderings of R objects or N objects, R objects taken from a group of N distinct objects is denoted by NPR or N permute R. We're going to write that down. N objects permuting R at a time. So for example, that last thing we did, last problem we did, we say we have 12 runners and we are rearranging 3 at a time. Okay, so for gold, silver, and bronze. Or in the first example, we said we had 12 runners. We don't know how many ways could you permute or order all 12 of them. And so this is the kind of quick way to abbreviate this. But this formula to calculate this is actually this formula right here. And it would have made our jobs a lot easier, even though we could still write that out. But we read this as N objects permuting R at a time or ordering R at a time. But we say it always comes out to be N factorial, or total number of objects factorial. So we say total from the total factorial over the difference between the total and how many we're ordering at a time. So taking a look at this 12 permute 3 example that we just did, we said this would have come out to be 12 factorial over N minus R, so 12 minus 3 factorial, which comes out to be 12 factorial over 9 factorial. Now, I want to be really careful here. This is not equal to, well, 12 and 9 share a common factor of 3, so wouldn't this be 4 factorial over 3 factorial? This is not true. Do not do this. But really, when we say 12 factorial over 3 factorial, we're saying 12 times 11 times 10 times 9 times 8 times dot 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 times 2 times 1 all over. Now on the bottom 9 factorial, we say 9 times 8 times 7 times 6 times so on and so forth. But what you'll notice is this, 9 and everything after down to 1 cancel out with 9 and everything after down to 1 up here, and what we're left with is the 12 times 11 times 10 that we had in this example that we had taken a look at here with our runners, if I can find it. This, okay. So it would have made our jobs a lot easier. Now what you might be saying, okay, so what about this 12 permute 12? The first time we did this, we had 12 factorial and 12 factorial here came out to be 12, times 11 times 10 all the way down to 1. And that was like 479001600 ways. Could we have used the formula there? And the answer to this is yes. We say 12 permute 12. 12 permuting all 12 at a time would have been n factorial. So in this case, we say n is 12. We say 12 factorial. Over now, here's our objects, the number of objects we're permuting. 12 minus 12, or n minus r factorial. So we get 12 factorial over 0 factorial. But by the definition we've already stated, we say 0 factorial is by definition equal to 1. So we still get 12 factorial as we did in that first instance. So what I've got here is I've got a whole list of factorials, actually 6 of them over here that I wanted to calculate. It's kind of appropriate, seeing as how n is 6 on all of these, but just kind of some special patterns that I wanted to point out using our formula. So let's start with 6 permute 5. We say 6 objects permuting 5 at a time. Using our formula here, let's choose a darker color here, we'd use our blue. We'd say 6 factorial over 6 minus 5 factorial, which comes out to be 6 factorial over 1 factorial, or really just 6 factorial. Okay, and this is of course something that we can calculate on a calculator. We say 6 times 5 times 4 times 3 times 2 times 1, or we could have just typed in 6 factorial, but we get 720, excuse me. So this expression here evaluates out to be 720 different ways that if I gave you 6 things, you could rearrange 5 of them at a time. So what if we said, okay, so I've got 6 objects, I'm rearranging only 1 at a time. This is kind of a special case. We see that we get 6 factorial over 6 minus 1 factorial. I'm already thinking of my answer here. 6 minus 1 factorial. So we get 6 factorial over 5 factorial, which if we write this out, we get 6 times 4 times 5 times 3 times 2 times 1 all over now 5 factorial. And this 5 factorial, you get used to this canceling out thing, but these 5 and everything after down here cancel out 5 and everything after down here, we get just 6. But if you think about this, if I gave you 6 things and I said rearrange 1 at a time, well, you could rearrange the first thing, that you're done. Rearrange the second thing. Well, you're only rearranging only that second thing, so you're done. You could rearrange each one thing one time. This is a really weird thing, but if I said, okay, so now what if I give you 6 objects, these 6, say, lines here, I say rearrange none of them. How many ways could you do this? There's one way to do that, and that is to just leave them alone. So using our formula for factorial, again, I just want to see how this works out. We say 6 factorial, which is our n, over 6 minus 0 factorial. This is the same thing as 6 factorial over 6 factorial, and of course that just comes out to be 1, since anything divided by itself is 1. So one more really interesting example is this. 6 factorial, 6 things permuting all 6 at a time. So we say 6 factorial over, in this case, 6 minus 6 factorial, which comes out to be 6 factorial, of course, over 0 factorial. But that's the same thing as 6 factorial over 1, which is just 6 factorial. So really to say 6 things, rearrange all 6 at a time, goes back to our original definition. We said, oh, hey, look, if you have 12 runners, basically there are 12 factorial ways that they can finish this phrase. And in the letter E and letter F, those are things you could pause a video and attempt on your own. But I want to take a look at an example problem here before we kind of leave this video of what I use, permutations. But let's consider this second situation here where it says we're considering 10 different colleges. Before we decide to apply to any of these colleges, we want to visit some or all of them. So in the first instance here, we say, in how many ways or how many orders, this is important, permutation means order, how many orders can we visit 6 of the colleges? Okay, so the first thing we're going to do is this. We're going to say we have 10 colleges total. We want to rearrange or see how many orders we can put 6 of them in at a time. So this is 10 objects, 10 colleges, permuting 6 of them at a time. So using our formula here, which was n factorial over n minus r in parentheses factorial, we get this. We get 10 factorial over 10 minus 6 factorial, which is 10 factorial over 4 factorial. So we are going to simplify this now. 4 factorial. So keep this in mind. We say 10 factorial over 4 factorial. I don't want to have to write all this out. 10 times 9 times 8 times 7 times 6 times 5. I don't want to write it all out because when I write out the bottom here, I just want you to realize this. You know, get used to this canceling out thing. But this 4 times 3 times 2 times 1 that I didn't write out on the top, I didn't write it out because this 4 times 3 times 2 times 1 is going to cancel out with those up here. And what we're left with is just this quantity here, 10, 9, 8, 7, 6, 5. So we say 10 times 9 times 8 times 7 times 6 times 5, 151200. 151200. Ways that we could, different orders we could visit 6 of those colleges in. And then the last example here, we say, well, how many ways can we visit all 10 colleges? I want you to recognize that this would just be 10 factorial. You know, we could visit 10 colleges as our first visit, but only 9 then colleges remaining to visit for our second visit, and 8 after that, and so on and so forth. But we could also say this is the same thing as 10 colleges rearranging 10 at a time. And again, this comes out to be 10 factorial over now n minus r, so 10 minus 10 factorial, which is the same thing as 10 factorial over 0 factorial. But again, the definition of 0 factorial is 1. So this just comes out to be 10 factorial, which in this case, just using the factorial button this time on our calculator, we say 10 factorial, we would get 36288, 36288, 3628800 ways. So yeah, this is just kind of a video on how you would use permutations in the formula.